I'm super excited to introduce Dr. Kristy Spencer, who works at Los Alamos National Lab in Criticality Safety. Crit safety is one of those areas that we really don't have a lot of exposure to here at UW, so I thought it'd be great to schedule something in our seminar list, and so we could all get a better appreciation of that and hear what's going on at the labs. And I know Los Alamos is one of the places, I feel like there's only 2 or 3 places where there's a really heavy, I mean, there's crit safety going in everywhere, but Los Alamos definitely has a major investment in crit safety. And so it's a great place to hear from. So Dr. Spencer got her degrees, including her PhD at Texas A&M. Spent some time interning at Oak Ridge, but for the last few years has been at Los Alamos working in this area. So excited to hear more about it. And with that, I'll turn it over to you.
Thanks. Go ahead and share my screen. So hi, everyone. First, I wanted to start off by thanking you for inviting me to talk about my work. I think it's really awesome that y'all are doing this. I know, at least for Los Alamos, we're a small, isolated town up on top of a mesa, and it's really neat to be able to talk to y'all from over 1,000 miles away during a pandemic. So just thank you for that. I guess y'all already heard my bio. A little bit to add. I got into nuclear because I wanted to work on interesting problems that help people. I was especially worried about climate change, like most of us. And I really started in the advanced reactor area. After undergrad, I was doing a Fulbright fellowship in Switzerland, and Fukushima happened that year. The reaction in Switzerland was a lot more pronounced than we had in America. And I was actually living on site of the Institute. So I was seeing protesters like every day on my roll home to the guest house. And I really enjoyed doing the work for advanced reactors, but I realized that nuclear has some issues that we do need to focus on now, so that way the public can accept us to help out with climate change in the future. So for both my master's and my doctorate, I focused on used fuel management. In this section, I'm just going to focus on my doctoral work, where I designed a new method to find optimal loadings for patterns and dry cask storage. This is important because the United States currently does not have a long-term nuclear waste management policy. This was the case in 2017, and still the case now. In its absence, dry cask storage has become the de facto option. And the way that most reactors deal with this is that they take the oldest and coldest used fuel assemblies from the spent fuel, and they move that to dry cask storage. But this means that at the end of your reactor lifetime, you'll have a bunch of really hot assemblies left in the pool. Back in 2006, the IAEA cited a need to move toward more sensible mixtures, so that way you didn't have that happen. This research was possible because of UNF standards. This is a unified database maintained by the Used Fuel Group at Oak Ridge National Laboratory. It's a MySQL database, and it contains information for over 150,000 individual fuel assemblies. It has reactor operation data, site attributes, cask design data, cask limits for certificates of compliance. And it has all the information that you need to run really detailed optimization scenarios for dry cask storage. So I implemented the tool in a Python package specifically to be integrated with UNF standards. So a little bit about the dry cask bloating problem. It's a combinatorial problem which are notoriously hard to solve. It's highly constrained and it's multi-objective. The three objectives we chose to focus on during my doctorate was to minimize the number of casks that you need to store all of the fuel over the entire reactor lifetime, to minimize the average initial heat load of each cask when you're loading it, and then to minimize the maximum time to transport. These are constrained by a few different things. So you have physicality constraints, such as the no replacement constraint. You can only have a used fuel assembly in one cask at a time. You also have cask capacity constraints that you need to respect. Casks have assembly selection constraints. So these are things such as burnup, like a total heat load for the cask or a per assembly heat load for some casks which use zone bloatings. You also have spent fuel pool constraints. So you can't have fuel in the pool after you've decided to have the pool shut down. And then you also have capacity constraints in the pool. And we kept some spots open always, what's called the full core reserve. And this is basically in case the reactor needed to shut down, all of the fuel could just move to the pool if it needed to. And then you have operational constraints. So you can only load so many casks in a given time period. It's a little bit faster once you've shut down your reactor, but it's still, you have to be safe. You have to be careful when you're doing the transfer. So it takes time. And then you also have minimum fill limits. So utilities won't want to open up a cask just to put a couple of assemblies in there. And we set this minimum at 75%, but utilities will actually want to completely fill up their casks. So this problem is formulated very much like a bin packing problem. And there's a lot of research out there looking at different optimization problems that you can use for bin packing problems. But this problem is a little bit different because we have a timeline that we're having to deal with. And also the assembly characteristics are time dependent. And that's not something that you see with normal bin packing problems. The original way that I was going to approach this was to survey some of the more well-established optimization algorithms out there and then just choose the best one for the job. But I found that the ones that were out there were having a hard time dealing with that dynamic component of the packing problem. So I ended up bringing together different aspects of multiple algorithms. And this type of combination is called a mimetic algorithm, which I named the new algorithm, the grasp-enabled adaptive multi-objective mimetic algorithm with partial clustering, which is a lot of words, but the acronym is Gamma PC, so that's pretty easy to say. And the operators in this algorithm are shown on the screen. We have different operators to either explore the search space or to narrow in on a specific region to find the best solution in that specific region. And so these just go until you find a set of good solutions. With multi-objective optimization, you won't just find one solution because the different objectives have trade-offs. So I implemented it in the Python package, and then I tested it out on a few different scenarios. I'm only going to talk about one of them here. Zion Nuclear Power Plant is a power plant that shut down in 1998, I believe. So they had all of their fuel just sitting in the pool for a while. And this was a unique opportunity because they actually moved everything into dry cask storage in 2015, I believe. And so they had a real world loading pattern that I could compare to. And they spent thousands of hours coming up with this loading pattern in order to minimize the dose at the site boundary. So they gave a really high quality solution that I could compare with. The solution that they came up with is shown in the graph at the right. They had the purple dot. The pink dots are all the solutions that Gamma PC found. And you can see that there's an indirect relationship between the number of casks and the average initial heat load. This is expected. Something that was surprising is that everything ended up having a maximum time to transport in 2025. And it turned out that this was because of that loading curve. Individual assemblies were driving this function instead of the loading configuration. So this slide is just pulling 3 solutions out. We're looking at that basis function, which is the real world loading configuration. We have what we're calling the recommended solution. This has the minimum number of casks. And then we have an alternate solution, which is just looking at if you've used a couple more casks, how would that impact your average initial heat load? And you can see that the top part, which is looking at the initial heat load, there is a much wider distribution of the heat load for that recommended solution compared to that real world configuration, but the median is lower. And then looking at the alternate solution, the maximum heat load is a full 2 kilowatts cooler than it is in that real world configuration. The bottom graph shows the time to transport. These distributions look very similar, and it turned out that most of the casks were ready to go as soon as they were loaded. It's just that some of them had to be delayed based on individual assemblies. So these plots show the same information just for the real world solution versus the recommended solution that Gamma PC found. These are as a function of time. So you can see that the average initial heat load for Gamma PC is on average lower across the timeline, but the distribution is more varied. And then for the time to transport, as soon as some casks are loaded, they were ready to be transported, but some of them had to wait. And again, that was based on individual assemblies and instead of the loading configuration. And that's not a place that you want to be with objective functions. You want them only to relate to your decision vector and not on external factors. So this slide looks at just the hottest cask in those 2 solutions. And you can see that the Gamma PC solution found a hottest cask that was about 1 kilowatt hotter than that real world configuration. Something to point out is that you will usually have empty spaces in your casks because your number of assemblies won't directly line up with the number of spaces that you have. It's important to put those empty spaces in your hot casks in order to reduce your maximum. So this is not something that Gamma PC was looking for, but it is something that I recommended to the used fuel group that they include in the future. So in general, Gamma PC was shown to perform well in the validation case, but also against testing solutions in the other cases that I looked at. I also generalized the problem to, it was actually baking a set of cookies, and the cookies cool over time and you have to put them into boxes. And that test set allowed me to compare Gamma PC against those well-established algorithms, and it was shown to perform well in those cases as well. For the nuclear scenarios, we saw the main improvement in the average initial heat load. And then that third objective, the maximum time to transport, was shown to be sensitive to individual assembly characteristics, which this is just an opportunity for the group to improve that objective function. And then the Zion test case highlighted that there was variability in the cast characteristics. So that could be another objective function that the group adds in the future. But considering that Zion Solutions spent thousands of hours coming up with their loading configuration, and I came up with that solution in, I think it was 12 hours, I think that Gamma PC shows a lot of promise for finding loading configurations. So that was my PhD. It was focused mainly on the back end of the fuel cycle. At LANL, I've been able to work with all different parts of the fuel cycle outside of reactors. I included this quote from ANS 8.1 on the slide. This is like the standard that governs everything that we do in crit safety. So it says, before a new operation is begun or before an existing operation is changed, it shall be determined that the entire process will be subcritical under both normal and credible abnormal conditions, which, to rephrase it, our job is to make sure that our operators go home safely at the end of the day. So I've been talking for a little bit now, and I thought it would be a good time to have a little audience participation. I have this brain exercise here, and I have the chat window open, so I'm hoping to get answers from y'all. Which system do you think has a smaller safety margin? So the one on the left is just a ball of plutonium. It's hanging out on a string in the middle of the air. And then the one on the right is optimized array of uranium, and it has water reflection around it. So what do y'all think? Okay. Anybody else?
You're not being graded here. Come on, make a guess.
Yeah, this is just for fun. Okay, so we have a couple for PU, and then one for uranium. Anybody want to say why they're thinking the uranium?
I'll take a guess.
Okay.
You specified it's an alpha phase, and isn't that the one that like will switch to the much denser delta phase at like just above room temperature?
Alpha phase is the more dense one.
Oh, okay. Then I change my guess.
Okay. Anybody else want to say why? Okay. So the reason that the uranium is not as reactive, I didn't say this, so this is probably a little trick, but the array for uranium has been optimized to maximize the reactivity. So if you move those rods in any way, you're going to have less reactivity. However, on the left, we have a ball of plutonium. If this, strings are not very strong, and if it dropped into a bucket of water, 5 kilograms is all you need to have a critical system with plutonium. So you have more than enough mass there to have a critical system. So that example is just a fun way to show that interaction of different parameters can sometimes lead to counterintuitive results. And a couple of the parameters that we deal with are shown in this plot. This is called a bathtub curve. And we deal with operations that are all along this curve. This curve shows the minimum critical mass depending on how much plutonium you have in your system. So this curve allows us to set easy mass limits, but you have to first determine where you are on that curve. So usually we're using MCMP to figure out the safety of the system along with other previous data. So we spend a lot of our time evaluating operations, and because we are a support organization, we also do procedure reviews, operation reviews, we respond to potential process deviations, and we do training of our operators. And something to point out, we have never had a criticality accident based on a bad calculation, but we have had several. I think between the 50s and 70s, we had something like 15 just for processing accidents. And these, they had bad procedures. They had procedures that didn't include the limits. The operators didn't understand what was happening. And so it's our job to really build that relationship with operations, so that way that one, they kind of understand how different parameters can affect their system, and two, that they feel comfortable enough with us that they can call us when they think that something is wrong. And most of our operators have only high school education. So we need to make sure that we're good communicators. The nice thing about this job is that we get to see so many different things that happen around the lab. I'm highlighting a few of them here. So I'm qualified in science and technology operations. They do detector development. They do IAEA training courses. They also have some uranium processing and machining. I'm pursuing another qualification for CMR. This is our chemistry building. So they have a lot of analytical chemistry, non-destructive assessments. We found out a couple decades ago that that building was actually built on top of a fault line. So we're in the process of trying to pull out everything from that building. The part of the building that is directly on top of the fault line is completely empty now, but because this building is so specialized, it's just taking longer to get other areas out of the building. And then we also have the plutonium facility at LANL. They do pit manufacturing, plutonium recovery, stuff like that. And I generally help out with the more virtual operations for them. So like movements of material around the facility. And this is because for some reason in the 1970s, when they were building the facility, they didn't incorporate ADA compliance into the building, you know. So I can actually get in there with my wheelchair, but most of our work is actually in that facility. So that's the day job. My division leader likes to say that's the part of the job that pays the bills. One of the fun things that I get to do is I'm leading the Whisper 1.1 software quality assurance. Whisper is a tool, a sensitivity uncertainty tool for MCMP. And as a part of that software quality assurance, I'm going through all of the input files that we use in order to determine the bias and just making sure that they are matching up with the experiments. So I wanted to make sure that we have common terminology before I proceed. We use what's called the upper subcritical limit a lot. This is starting at critical, you add in your bias, and this is always a negative bias. We don't use positive biases because they're not conservative. And then you subtract your bias uncertainty, and then a little bit extra, what's called the margin of subcriticality. For MCMP, this is generally 0.02. And there's some reasons for that. And then if you are working with a specific application that is not very similar to the benchmarks that you used to determine the bias, sometimes you need to add in a little bit extra margin just to make sure that your limit captures everything. So this is a very brief introduction to Whisper. The way it works is that MCMP determines the sensitivity profiles for the cross sections for a specific application or a benchmark. And then Whisper takes those profiles and data covariances to select a set of similar benchmarks. And then it calculates the bias uncertainty, and the margin of subcriticality in order to set an application-specific USL. And this is pretty cool because traditionally the way we do it is we just take a whole bunch of benchmarks and we come up with the USL, and then we say, this USL is the one we're using forever. So Whisper is an evolution of that philosophy. And all of our models are drawn from the International Handbook of Evaluated Criticality Safety Benchmark Experiments. So when I was doing the reviews for all of these benchmark models, I realized that we would need to change a lot of them. And I didn't want to just do that in a vacuum because the Whisper team was sharing everything. And we found out that there are multiple critical benchmark collections at LANL, and they're all believed to have a common origin. And so I teamed up with the MCMP team, the nuclear data team, to create the Los Alamos benchmark suite. And this is an effort to centralize the benchmark models. And we're implementing a formal review and revision process in here just because before there was no documentation about where the models came from. And so we're making sure we're writing down who's reviewing it, who's revising it, and why we're making revisions. And the nice thing is, because I was already doing the software quality assurance for Whisper, all of those reviews were set to go, and we're able to set everything up using that benchmark suite. So all of the reviews are two-person reviews. All of the revisions are also two-person revisions. And the number of revisions that we need to do is shown in the graph at the right. And I broke this up into different types of revisions that need to be done. So some of them are completely fine. They just need to be added to the GitLab repository. Some of them needed policy changes. So this is things like, we only model oxygen using oxygen 16. But it's not really something that's wrong with the model. Some of them had written down the benchmark K-effective incorrectly. And this is really important if you want to calculate your bias. And then I just lumped everything else together. And the purple shows everything that we have finished merging into the repository right now. Considering that the reviews took 4 years to complete, and we started this back in May, I think that we're making really good progress. We have slowed down recently just because there's been a lack of funding, but we applied for nuclear criticality safety program money, and hopefully we'll be able to get back to doing a lot. We did last month finish up all of the plutonium revisions. This was a priority for us because of the plutonium fabrication facility. And these are initial results from that effort. We wanted to just see what was the impact of all of those changes. So the plot shows the bias before and after revision. You can see that most of the benchmarks didn't really change all that much. I think maybe 10 or 12% were statistically significantly different. And you can see that there's a small set that are like visually different, and those are all plutonium metal. And the nice thing is that they're all reductions in the bias. And these are listed at the right in the table. These are our top 12 largest changes. And you can see that one of them was just due to an incorrect benchmark multiplication factor, but the rest all belong to one benchmark series. This series had a lot of revisions in the MCMP models, but probably the biggest is that in the experiment, they had oil between their hemichells, and in the MCMP model, they didn't use the S-alpha beta card for the oil. And so we added in the polyethylene S-alpha beta because the hydrocarbons are similar. And I think that made the most difference for PU Met Fast 42. So we have the plutonium ones done. We still need to do the rest of Whisper. And then once we're done adding Whisper, we want to keep going. I think the handbook has more than 4,000 different cases in it, and we would eventually like to have all of those in labs. We have some models that were generated by another organization, and so eventually we would like to add all those. That is a significant chunk of work that will need to be done, considering that it took us 4 years just to do 1,100 input files. And in addition to that, we want to add new benchmarks as they're added to the handbook, and also make sure that we're keeping up with any revisions for models in the handbook. So this effort is supporting multiple projects at the lab. And one of them is this benchmark intercomparison project. This is a collaboration between Los Alamos, Oak Ridge, Lawrence Livermore, and IRSN, which is like a French lab. And this study that I'm presenting was from last year. This is just looking at how different USLs are generated by the different codes that we have. So we looked at 4 applications just to see what USLs would be generated. There was a uranium metal, uranium solution, plutonium metal, and plutonium solutions. And these are kind of representative of areas that we're concerned about. We do expect there to be differences in the USL, and this is for a number of reasons. We have different benchmark collections. We have different ways of selecting the benchmarks. We also have different methods of calculating bias and bias uncertainty. For example, Whisper uses extreme value theory, but USL Stats uses generalized least squares. And then different methods for calculating K effective, and that's based on the codes. We also use different sensitivity profiles, and the way that we handle that margin of subcriticality is different. So this table kind of just summarizes all those differences. You can see that the size of the suites are very different. The covariance data is also different. And this slide summarizes all of the percent differences in calculation margins. I'm looking at that because the calculation margin is just the bias and the bias uncertainty. So that kind of removes the differences in the margins of subcriticality. And you can see that the uranium solution has the biggest difference between the different results. So this table shows the breakdown of that USL calculation. So it shows the bias uncertainty, 1 minus the calculation margin, and then the USL. And you can see that the bias that we got at LANL was the largest. And we're thinking that this is probably due to the inclusion of a couple of benchmarks that have higher biases associated with them. But the benchmark sets that were chosen by the different codes, they don't have a lot of overlap. You can see that in the Venn diagram at the bottom. And the reason for that is unclear. Looking at the uranium solution, again, the LANL one has the highest bias and bias uncertainty. IRSN calculated a positive bias, and so we just set this to 0 to avoid a non-conservative USL. And then you can see that LANL has the highest calculation margin. And we're thinking that this is also due to another benchmark that had high uncertainty. Also, the Oak Ridge set included some benchmarks that were much more similar to this application case. These aren't in the LANL library, and so this is just a reminder that it's important to have benchmarks in your suite that are very similar to your application case, because otherwise you might be generating an overly large bias. These are the results for the plutonium metal. And here you can see that again, we have the largest bias uncertainty, and the other two are very similar to each other. So one of the reasons is that we included PMF42 in our set. And this was before we finished up doing those revisions. If you remember PMF42, that was the one that had all those really large reductions in bias. And so this is an important reminder that the quality of your models is really important when you're trying to understand how well your code is performing in terms of different parameters that you're interested in. Another interesting thing is that both of the other ones did choose PMF5, and this had tungsten in it with a rather large sensitivity to tungsten. While Whisper didn't choose PMF5, it did choose MMF5, which also had tungsten, but the sensitivity was a lot lower. So that was just an interesting result for us. And we wanted to look at what would happen if we forced Whisper to choose all of the same benchmarks that the Oak Ridge team chose. And these are the results for this. You can see that the calculation margins are a lot more similar. We are calling out that normally Whisper applies a non-coverage penalty when your application isn't very similar to your benchmark set. But for this, we took that out. And then if we're choosing the same set of benchmarks, we wanted to know how do they rank the different benchmarks. And you can see that while the first three benchmarks are the same, after that, the different ranking systems are different. And this is because the correlation coefficients we're calculating are different. This could be partly due to the different covariance data that we're using. But if you look at that PMF5, if we force Whisper to choose it, it calculates a correlation coefficient of 0.65, which is really low. We wanted to see what would happen if we took tungsten out of that model, and the correlation jumped up to 0.91. So there is probably more than just the covariance data that's different. And then for the plutonium solution, we again had the largest bias. The other two had positive biases. And we're thinking that part of that is we included a specific case that the other two didn't. But overall, this shows that when you force the same benchmark sets, the codes are very similar to each other. So to just kind of summarize everything, Gamma PC is a mimetic algorithm that I developed for the used field group at Oak Ridge National Laboratory. It's specifically developed for UNF standards. I'm working at LANL now, and I am dealing with different parts of the fuel cycle. It's really neat to be able to see all the different things that go on at LANL. But the primary goal of the Nuclear Criticality Safety Program is to prevent criticality accidents under all credible scenarios. And then the Los Alamos Benchmark Suite is a collaboration between NCS, MCMP, and the nuclear data teams to build one high quality benchmark suite for us to use at LANL. And eventually we would like to roll it out to the rest of the community. And then just taking everything at a really high level, this is all about data. So for Gamma PC, it was developing a adaptable mathematical framework so that way we could apply that optimization to any reactor site around the country. And the group is currently submitting that tool to RSIC, which is pretty cool to know that the work I did as a grad student isn't just going to sit on a shelf somewhere. And then labs, instead of using data better, it's building better data, building high quality benchmarks to improve the understanding of bias and to help reduce those confounding variables to understand differences in codes better. If y'all have any questions over the next few days, please feel free to email me. I have my email on the slide, and I just want to thank y'all again. Thank you for the attention and the opportunity to talk with y'all. Are there any questions?
Thanks so much, Kristy. That was really interesting. It's got a lot of questions about crit safety always, and so it's good to get some of those things there. Let me see if there's any questions from the audience. Go ahead and unmute yourself if you have questions. Or otherwise, I'll go ahead. So one of my questions that I'm often curious about is, the geometric fidelity of modeling that's used in practice for criticality safety. A lot of these benchmarks are fairly straightforward geometrically. And so matching the benchmarks to the experimental measurements and things like that, it's not usually confounded by geometry. Although I've seen, I think Jeff Favorite gave a talk here a couple of years ago about sort of fine tuning the geometric representation of Jezebel and things like that. But when you go into the field, then you're actually, you've got a near critical system in a hot cell with an operator and all the complexity of that geometry. How do you account for all of those details?
So part of it is we make overly conservative simplifications, and we have some ways that we can incorporate all of the reflection from walls to people to glove boxes. One trick is we just wrap the material in water. About 1 inch of water is enough to account for most of the reflection that will be present. And then if we really want to make it ultra conservative, we put it in 12 inches of water, which is practically infinite reflection. So that's one way we do it. Sometimes if we've made the model too conservative, and we have to scale things back to be more realistic, that's when the models get a lot more complicated, where we start building that glove box completely in the model, or building the containers to be more realistic. For me, I've had a couple of scenarios where there's been a frame to enforce spacing, and I've built the frame completely in MCMP, and those are a little bit more difficult. But for those operations where the overly simplified, very conservative model works, then that's always nice for us.
So does that mean there's a philosophy of wanting to have so much margin? I mean, I guess in a lot of other places, there's a desire to whittle away at that conservatism and that computational margin because there's performance benefits to be gained from having less conservatism. Is that less true in this domain?
I think for us, in 2013, we had a shutdown of all operations, and coming back from that, we have just been naturally more conservative because we wanted to make sure that everything was good. As we're starting to ramp up some operations, we're having to relook at that level of over conservatism. and our we call them gray beards, like our wise experts in the field are helping us develop like how do we step back from that conservatism. And this, when you start out in this field, I think that we're all naturally more inclined to be conservative because we don't want to make a mistake. And our division, during that shutdown, we went down to one person in our division. And so we have a really young division. And so we're starting to learn from our experts, how do we step that back?
Okay. Thanks. Other questions? So in the Gamma PC work, I was trying. I think I had a question we talked about, but I forgot about it now. No, it's left me. Sorry. I mean, that was really interesting work to. I mean, it made me think of some of the things we do in cyclists, right? And adding. I don't know if you're familiar with cyclist modeling fuel cycles, but we've got our own sort of optimization layer in there that's at a different place. But it would be interesting to look at wrapping Gamma PC as a cyclist tool to handle that part of the fuel cycle, to be able to model the placement of assemblies into casks as part of that. And so something I'll have to think about and see whether there's an appetite for anything like that.
Yeah, one of the things I was thinking would be to connect it to transportation studies, just because the loading configuration was very based on what the utility needed, and it didn't have that. It kind of had a long-term view by including that loading curve into it, but I think connecting it to a longer term study would be really interesting to see how those configurations might change.
Yeah. Do you think that the constraints that transportation would place on the loading patterns would be qualitatively would be qualitatively different than the heat load constraints or dose constraints?
So the loading curves are more about criticality, and like they do have some heat load constraints built into them, but I think that their primary concern is like if something were to fall into water during transportation, that if the water ingressed into the cask, it would be fine. And so I think that's primarily what the loading curves are for.
Okay, all right. Sure. All right. Well, last call for questions. All right, well, thank you again. Thanks so much for sharing that with us. And yeah, we'll send you the link to the recording to get it approved for us to share with people as well. So
yeah, thank you.
Right, thank you. Have a good afternoon.
You too. Bye, y'all.
Bye, everyone.